So, all right. Now comes a slightly more complicated thing. So, we'll just write down what this four boundary condition after you explicitly substitute these electric field and magnetic field. Okay, and we already figured this out, so these are straightforward. This. Okay, but do I have all this? But yeah, I still have all the electric field, magnetic field. Now you just plug in all these into here. So so the first one you have D is epsilon E for this omega, right? So for the first equation, so you have epsilon E sub 0, and you forget about all the phase now because we already match all the phase at the same, all the terms. Okay, and so that's in the lower boundary, in the lower medium. And then you have the refracted wave, right? But the refracted wave have the same epsilon. So so D has the same epsilon. So you basically this is in the same medium. So E0 double pi with the same epsilon. And then over on the top medium, and you need to subtract them because this is a jump condition. So minus epsilon pi E0. That equals to 0. That's the first equation. Yeah, that is the first equation, 7.37. Okay, so that's straightforward. Now the second equation is B. B is given by this one, so you have absolute value of mu epsilon, but K cos E0. Right. And now I forgot this dot N. Dot N. Dot N is just like dot C. N is a 0. But that's fine. Now for this one, you have B, so it's so the same thing here. So you have mu epsilon, and you have two terms in the lower medium. They have the same mu and epsilon. They have K univector cos into E sub 0, and you have KC double pi here cos into EC double pi, and then subtract the upper medium pi epsilon pi. K pi cos into EC pi. And this one, the whole thing, dot in the end, 0. I cover everything. N is a C, N is just a C. I mean, this is the second equation. I mean, this is if you want, you can actually go back to this one instead of writing it. Jackson will using this one instead of this one, and change that to K, and this is K double pi. All this is doing is just already substitute the dispersion relation in here, but either way is fine. You get exactly the same result. And Now the third one is cos into n. This one should be straightforward because you have E0 plus E0 double pi on the lower medium and minus E0 pi on the upper medium. Cos into n, that is C. The third one is straightforward. Now the last one is H. H is B over mu. So B over mu, you can either say K divided by mu or just like Jackson knew, or if you use my notation, divided by mu is just basically the square root function becomes epsilon over mu. And you have K cos in the E0 plus K0 double pi in the E0 double pi and minus epsilon pi over mu pi in square root cos in the E0. Okay, and then everything cos n equals 0. Okay, so these four boundary conditions of right, you can write out the explicit relationship between all these unit electric field. So you have an electric field, instant electric field, the refracted electric field, and then the refracted electric field. And the goal of the exercise is to express the refracted and refracted electric fields, the E double pi, E pi in terms of E sub 0. And the incident, obviously, the incident angle or the K, right? And we already figured all the angles, so it's basically the geometry is fixed. Now we need to figure out how this magnitude or the amplitude of the reflected or refracted wave in terms of the incident wave. So that's the goal. And it's basically to solve this four equations to get those relationships. And these four are not, turns out to be not totally independent. They sometimes only three, you need to use three of them. One of them will give you repeated condition. And now these are in vector form, and which are more difficult to use. If you manipulate that to try to solve E0 pi and E0 double pi this way, you get a lot of vector operation which are complicated. The easier way to do it is using component form. In component form, basically you're writing your electric field in terms of your component. So there are generally two possibilities. Basically, the wave has two kinds of polarization. So you consider one polarization at a time and derive your relationship based on the polarization. And in our case, it's much easier to use separate into two linear polarization. That turns out to be relations much easier, much less complicated. So we'll divide that next time because we are about time. So basically, just point out the separation. So one polarization is that the electric field is along the y direction. So that is figure 7.6, the upper figure, the A panel. So electric field is pointing inside. So basically, the first case is E is in the y direction. If E in the y direction, I should say all the E, not this should be the upper one should be E pi. If E is in along the y direction, that's the first case. And the second case is the opposite, is the B along the y direction, because E must be perpendicular to B. If B is along the y direction, it means that E is on the xz plane. The vector must be on the xz plane in order that the direction of E is perpendicular to B. So that's the second case. The first case is E is perpendicular to the XZ plane. The second case is X is along the XZ plane. Okay, and we separate that and use these four relationships to divide the relationship between the incident wave and the refracted wave. And all these are algebraic consideration and some geometry. So nothing very advanced, but it's just need some time to solve the equation. So, but we'll struggle with that next next Monday.